At 03:12 in the morning on November 25, NASA released a revised velocity report on 3I-ATLAS that stunned every observatory tracking its arc. The object was confirmed to be moving over 2,000 times faster than the relative drift expected for interstellar comets within our galactic frame. This wasn't a data artifact or miscalculation. It had been observed in 3 separate bands by independent instruments. And that figure, 2,000 times too fast, isn't just odd. It violates our current understanding of gravitational influence, orbital decay, and even basic relativistic momentum. Whatever 3I-ATLAS is, it's not just moving through space. It's ripping through the Milky Way like a controlled projectile, and Earth is caught in its shadow. The confirmation came at exactly 03:12 on the morning of November 21, 2025. NASA's Jet Propulsion Laboratory finalized their velocity remeasurement of 3I-ATLAS based on triangulated telemetry from multiple orbital platforms and deep space arrays. The figure wasn't just unexpected, it defied every principle of galactic motion that astrophysicists rely on. According to the data, 3I-ATLAS was travelling at a speed of 1.56 million kilometers per second relative to the galactic frame. That number isn't just higher than any previously recorded comet or asteroid. It's over 2,000 times faster than the standard relative drift of interstellar debris, which typically moves between 200 and 800 kilometers per second when passing through the Milky Way. The speed wasn't gradual. It wasn't accelerating incrementally. It was constant, steady, and directional, mapped over a series of consecutive tracking passes across 3 instruments. How is this possible? The standard tools for measuring deep space velocity include Doppler spectrometry, radar echo timing, and reflected light phase angle computation. All 3 were used in this case. The James Webb Space Telescope detected a compressed light band signature from the object that did not redshift in accordance with normal angular momentum. The Goldstone radar facility pulsed the object and received a return signal in less than a millisecond, an echo that was consistent with a high-velocity object moving through a vacuum with almost no drag. And the European Space Agency's infrared tracking grid noted no delay between signal send and signal return, except for a subtle modulation consistent with forward-bending emission geometry. Put simply, every major observatory saw the same thing. A foreign object crossing the galactic medium faster than theory allows. Speed, on its own, does not indicate artificiality. There are natural processes that can accelerate bodies to enormous velocities, gravitational slingshots from supermassive black holes, close passes through neutron star binaries, even the explosive remnants of hypernovae. But 3I-ATLAS showed no trace of such an origin. Its trajectory did not lead back to a known high-energy event, nor did it exhibit the chaotic motion or rotational decay typical of such violent ejection scenarios. Instead, its path was disturbingly straight, a calculated vector across the galactic arm, passing through the heliosphere with no detectable curve or scatter, as if it had been launched, not thrown. That word, launched, isn't used lightly. It implies control, intent, engineering. And the implications of that are enough to delay formal publication of the velocity report by nearly 24 hours, as internal reviewers scrambled to rule out every possible source of error. They found none. The signal was clean, the triangulation was confirmed, and the physics, for now, remain broken. To reach this speed, a body the size of 3I-ATLAS would need to undergo constant acceleration over astronomical time, or receive a one-time push from an unknown propulsion mechanism. The kinetic energy required exceeds what any known object could contain passively. If it wasn't launched, then the universe just revealed a new type of object, one that violates Newtonian dynamics, Einsteinian relativistic limits, and perhaps the very principle of inertial drift. As of now, no agency is publicly committed to an explanation. The term being used internally is velocity anomaly, but off-record briefings acknowledge the discomfort. This object is not just an outlier. It is an outlier by orders of magnitude, far beyond the range of natural variation. So the question becomes, what is 3I-ATLAS and why is it moving like this? And deeper still, if it's moving at 1.56 million kilometers per second, where is it trying to go? Once the velocity anomaly had been confirmed, the next step was to verify it using a completely independent method. That method was Doppler spectrometry, one of the most reliable tools in observational astrophysics. If 3I-ATLAS was indeed moving through the galaxy at over 1.5 million kilometers per second, it would leave behind a unique fingerprint in the light it emitted and reflected. And it did. But not the fingerprint anyone expected. Normally, fast-moving celestial bodies produce a redshift when moving away from Earth, and a blue shift when approaching. This is caused by the compression or elongation of wavelengths, much like the change in pitch of a passing siren. For 3I-ATLAS, instruments on Earth and in orbit observed something radically different, a nonlinear shift across multiple bands, compressed not only in the visible spectrum, but extending deep into the near-ultraviolet and soft X-ray regions. Instead of showing a smooth gradient, the spectrum was compressed tightly, exhibiting a frequency jump inconsistent with known gravitational acceleration. The spectral lines were squeezed together far more than theory predicted. It was as though the object wasn't just moving fast, it was bending the rules of Doppler itself. The most startling element was what analysts called the violet squeeze. This phenomenon was recorded by the Hubble Space Telescope, the Solar and Heliospheric Observatory, and ESA's ExoMars orbiter, which all picked up the same signal. Emission lines from known elements like ionized magnesium and carbon were unnaturally narrow and shifted toward the violet end of the spectrum, but not at a consistent rate. Instead of a smooth Doppler arc, the wavelengths were folded. That's not a metaphor. The spectrum bent in on itself at 3 distinct frequency thresholds, creating a spiral-like compression pattern that researchers had never seen in natural celestial bodies. One proposed explanation was that 3I-ATLAS was emitting from multiple angular vectors simultaneously. In other words, the reflected light wasn't coming from a single coherent point source, but from several facets, each moving at slightly different trajectories, yet held together as a unit. This behaviour has only ever been observed in human-made probes using active magnetic field stabilisation to maintain orientation at high velocity. Then came the next puzzle: polarisation. Light from natural comets is often weakly polarised due to scattering off asymmetric dust particles. But the polarisation pattern from 3I-ATLAS was unusually strong, so strong in fact that it suggested coherent reflection off a surface smoother than any known natural object. This led to a new theory, that 3I-ATLAS was reflecting light from an engineered surface, possibly a composite material with variable reflectivity across bands. Combined with the violet squeeze and spiral Doppler compression, this kind of surface would produce the exact anomalous readings being recorded, a material that could compress light directionally, angle it off axis, and mask its true motion vector. The implications were sobering. This isn't just about speed anymore, it's about optical deception. If the light is being manipulated, compressed, redirected, masked, then 3I-ATLAS might be controlling its visibility. It might be hiding where it's truly going. And yet, even with the compression and phase anomalies, all 3 agencies, NASA, ESA, and the Chinese National Space Administration, agreed on one thing. The Doppler profile was coherent. It was not a glitch. It was not noise. It repeated identically across multiple passes over a 48-hour window and was confirmed at different incident angles from Earth, Mars, and Lagrange orbit. In short, 3I-ATLAS is not simply redshifting due to speed. It is emitting light in a pattern that suggests intelligent modulation. Some observers have already suggested this could be the first known case of non-random photonic compression, a theoretical technique for optical stealth. Whatever the mechanism is, 3I-ATLAS is not drifting through space. It's moving with intent, and folding the light behind it as it goes. At precisely 0148 UTC on November 21, 2025, the Goldstone Deep Space Communications Complex in California initiated an active radar sweep of 3I-ATLAS. It was the third such sweep in 48 hours, but this time the results returned something that forced mission control into a rare internal lockout protocol. For a span of 17 minutes, all telemetry data from DSS-14, the main 70-metre antenna, was withheld from public channels. What they had received wasn't a noise pattern or an incomplete echo. It was a perfect return, and it had structure. Radar ranging is a cornerstone of deep space navigation. A powerful microwave pulse is transmitted toward a distant object, and its return, delayed by the time it takes to bounce back, is analysed to determine distance, surface texture, and even motion. The time delay gives range, the frequency shift gives speed, and the signal degradation tells us about shape, rotation, and reflectivity. But when Goldstone pinged 3I-ATLAS, the return signal arrived in 0.096 seconds, a timing that placed the object at an unambiguous distance of 288,000 kilometres at the time of contact. That wasn't the anomaly. The anomaly was the shape of the return wave. Instead of a diffuse scatter indicative of a rocky, irregular comet, the waveform came back with high coherence. The signal was smooth, sharply bounded, and exhibited harmonic resonance across multiple return bands. In practical terms, this meant the radar wave had struck a surface, flat or gently curved, metallic, and possibly layered. The object reflected the radar pulse in a way that implied either internal framing or active phase cancellation. What shocked analysts wasn't just the clarity, it was the lack of scatter. Natural comets, with their dust and gas halos, almost always produce noisy returns. The coma acts like a fog, bouncing radar in random directions, but in this case, the beam punched through the coma and hit something solid, and it came back clean. Even more surprising was the echo phase pattern. Normally, a return wave echoes at a single frequency peak. This one had three: equidistant, equidominant, and symmetrical. The best match in Goldstone's database wasn't a natural object. It was the synthetic radar signature of NASA's own deep space test platforms, specifically the Voyager-class bus. That platform uses internal truss structures and dish reflectors that produce similar multi-point echo patterns. Was 3I-ATLAS showing the signature of a constructed hull? That's what radar engineers started asking. Internally, the shape of the return was described as trident echo, a name given when three dominant reflection points are spaced evenly around a central core. In most spacecraft, this occurs when you have a central spine with lateral appendages, solar panels, antennas, or magnetic scoops. And then came the frequency bleed. After the main echo, Goldstone recorded a faint harmonic tail, a slow fall-off of radio energy that seemed to phase shift in intervals. The tail was narrow, about 0.7 seconds long, and pulsed every 0.13 seconds across a narrowing frequency band. Engineers described it as chirped decay, a phenomenon normally associated with materials that are absorbing and re-radiating energy after impact. This raises a staggering possibility. 3I-ATLAS might not be passively reflecting radar. It might be absorbing it, processing it, and retransmitting part of the signal in a controlled cascade. If this interpretation is correct, it would be the first known object outside Earth's orbit to show active radar modulation. Not a bounce, a response. Goldstone has since reclassified all future tracking sessions under Tier 2 restricted protocols, usually reserved for national security space assets. No raw data has been publicly released, only summaries, and all internal references to the object now refer to it not as comet but as target. What they saw was clear, what it means is not. The universe operates according to laws, and when those laws break, or appear to, scientists don't change the rules. They test the measurements, they check the instruments, they exhaust every natural explanation before considering that something new might be happening. That's exactly what happened when NASA, ESA and CNSA tried to explain the acceleration profile of 3I-ATLAS. At first glance, the data appeared consistent with a textbook hyperbolic orbit. A fast-moving interstellar body swings past the Sun, gains velocity through gravitational slingshot, and exits the system on a curved outbound trajectory. This is what happened with Oumuamua and Tui Borisov. It's what should have happened here, but it didn't. Shortly after its perihelion, its closest approach to the Sun, 3I-ATLAS began accelerating again, and not in the direction solar gravity would predict. According to composite tracking from ESA's Mars Express, China's Tianwen-1 orbiter, and NASA's MAVEN, the object increased its velocity by over 4,000 meters per second in a direction perpendicular to solar wind vectors. That's not just unexpected, it's impossible under current models of orbital mechanics. The first theory was outgassing. When solar heat strikes the icy surface of a comet, trapped volatiles sublimate into gas and eject material into space, producing thrust. This is known to cause minor changes in trajectory, especially for fragile comets. But no one had ever recorded this kind of clean lateral acceleration from a body with no visible venting. Infrared and ultraviolet monitoring showed no thermal hotspots, no jets, no flare events. The coma remained symmetrical. The tail was short, consistent with passive reflection of solar radiation. not the signature of sudden explosive venting. No light curve shift was observed, no spin-up, no plume. The second theory involved radiation pressure. Photons from the Sun do exert force, enough to move very small objects over time. But for 3I-ATLAS, a body estimated to be between 1 and 3 kilometers in diameter, the force of solar photons is negligible. It would require a cross-sectional surface of ultra-low mass and high reflectivity, like a solar sail. But radar imaging ruled that out. The object had density. It was not paper-thin, and yet it moved as if something external was pushing it, with no visible cause and no trailing debris. When analysts applied momentum models, nothing fit. Angular momentum wasn't conserved. Gravitational models failed, and when the trajectory was simulated using JPL's horizon ephemerides, the deviation couldn't be matched with any known force in the inner solar system. That's when language began to shift. The word acceleration was replaced by velocity gain. The difference is subtle, but meaningful. Acceleration implies continuous force. Velocity gain can happen in a burst. It was as if 3I-ATLAS had experienced a single impulse event, a push. But where did it come from? There were no CME impacts recorded at the time, no shock waves, no known gravitational interactions. Mars was behind the object's flight path, not in front. And the Sun's influence was waning as the object moved outward. Eventually all three agencies issued similar statements. No current model of passive celestial mechanics could account for the post-perihelion trajectory of 3I-ATLAS. The term used by EA was kinematic outlier. NASA's internal report referred to it as a Type 3 non-ballistic path deviation, and China's CNSA, in its encrypted briefing summary, labelled it mechanically unbound. In simpler terms, this object doesn't follow the rules. When physics fails to explain motion, two possibilities remain. The models are incomplete, or the assumptions are wrong. But 3I-ATLAS didn't just challenge the models, it forced every gravitational simulation to crash, over and over. Something gave it a push, and no one knows what. Heat is hard to hide in space. Even the faintest mechanical activity, an engine firing, a thruster burst or thermal venting, leaves a clear signature. That's why orbital astronomers always turn to infrared first. It's the fastest way to spot what can't be seen in visible light. And for interstellar objects, it's the baseline test for determining whether something is active or inert. But 3I-ATLAS broke that rule. Following its unexpected velocity spike on November 21st, 3 separate instruments were immediately retasked to track it in the thermal band. NASA's NEOWISE telescope, ESA's Infrared Space Observatory, and the Chinese SkyMap infraarray. All 3 produced the same result. Nothing. No hotspots. No plume decay. No thermal gradient shift. The entire body remained within 0.2 Kelvin of its pre-acceleration baseline. For comparison, a natural comet experiencing even minor outgassing sees at least a 10 to 15 Kelvin jump in localized heat regions. But here, the infrared profile remains static. This is more than just surprising, it's physically inconsistent. If the object had accelerated by over 4,000 meters per second, there had to have been an energy source. That energy, even if only used briefly, would generate heat. Momentum requires force, and force produces waste energy, often in the form of heat dissipation. But in this case, no residual burn signature was observed on any surface of the object. Not from the core, not from the coma, not even from the dust trail. Analysts were left with 3 possible explanations. First, that the acceleration was illusory. But that theory fell apart quickly, as Doppler and radar tracking from Goldstone and Tianwen confirmed the trajectory change independently of thermal data. Second, that 3I-ATLAS was using a propulsion method not based on combustion, such as electromagnetic or gravitational vectoring. But even ion drives, among the most efficient propulsion methods, leave behind a thermal wake measurable in low Kelvin bands, and here there was none. Third, that the heat was there, but deliberately masked. Some materials are known to suppress thermal signatures, particularly in military stealth applications. These include metamaterial composites and nanoparticle-infused ceramics designed to deflect or absorb infrared radiation. If 3I-ATLAS were composed of such a material, or coated in one, it could, in theory, avoid thermal detection. But this technology has never been observed in natural bodies. Infrared scans taken 36 hours apart revealed no variance in heat dissipation zones. Even as the object moved away from solar proximity, its surface temperatures remained anomalously stable, hovering just below 250 Kelvin with less than 1% fluctuation. Natural comet surfaces fluctuate constantly with rotation and solar exposure. Even a dusty tail shows variance. But 3I-ATLAS didn't radiate heat like a comet. It radiated heat like a machine in standby. This led researchers to test for thermal reflection, whether the object was redirecting heat rather than emitting it. But again, no significant reflected infrared was detected from the surrounding space. The heat wasn't bouncing off, it simply wasn't there. If true, this suggests a highly advanced thermal regulation system, one capable of absorbing acceleration energy, converting it with high efficiency, and suppressing radiative loss to space. Some called this implausible, others called it impossible, but all agreed. 3I-ATLAS did not behave like a comet. It accelerated without igniting, it moved without heating, and it left no trace in the spectrum where heat leaves its mark. And that raises a more unsettling question. What kind of object exerts force in space but leaves no heat behind? Whatever 3I-ATLAS is, it's not burning, and it's definitely not drifting. Every object in space follows the same rules. At least that's the assumption built into every orbital model from Kepler to Newton to Einstein. Whether it's a moon, a satellite, or an interstellar comet, once you measure its mass, velocity, and proximity to gravitational bodies, you can predict its path. That's how we land probes on asteroids and calculate planetary flybys decades in advance. 3I-ATLAS didn't just bend those rules, it broke them outright. After the November 21st acceleration anomaly, teams at NASA's Jet Propulsion Laboratory and ESA's Mission Analysis Division independently ran orbital simulations based on updated telemetry. The goal was to trace the object's past trajectory and project its future path through the heliosphere. But neither simulation converged. Normally, when an object is plotted with a known set of variables, distance, speed, mass estimate, the resulting orbit fits a stable mathematical curve. But with 3I-ATLAS, small changes in the input data caused massive swings in the projected orbit. Some paths spiraled into the Oort cloud, others curved sharply toward the ecliptic. Several exited the solar system at steep, unnatural angles. The problem wasn't the software, it was the data. Even after correcting for gravitational assists, solar wind drift, and light pressure, the orbital path of 3I-ATLAS didn't stabilize. JPL analysts used high-fidelity N-body simulations that factor in gravitational influence from every major planet, the Moon, and even large asteroids. Still, the object's movement refused to align, at least not until they added a variable that doesn't belong in celestial mechanics: external impulse. When a non-gravitational force was artificially injected into the simulation, a discrete burst of velocity at a specific point in time, the orbital model snapped into coherence. The revised path traced a slingshot around the Sun followed by a sharp vector shift aligned 19.2 degrees off the ecliptic. The acceleration wasn't random, it was precisely timed to occur at the moment when 3I-ATLAS passed closest to Mars. There was no gravitational assist from the planet, but there was a maneuver. This changed everything. If an object can adjust its orbit mid-course, it's no longer a passive body, it's navigating. And the orbital data revealed something even stranger. Between November 16th and November 21st, 3I-ATLAS passed through what NASA calls a gravitational corridor, a narrow region where the pulls from the Sun, Earth and Mars nearly cancel each other. This is the same kind of corridor exploited by spacecraft using low-energy transfers and halo orbits. In short, it flew through the exact path you would choose if you were planning to conserve energy and reorient your trajectory with minimal fuel. That level of optimization suggests forethought, and orbital precision at this scale doesn't happen by accident. One JPL analyst reportedly described the object's path as intelligent trajectory compression, a term used in autonomous drone systems when a vehicle minimizes path length while retaining mission goals. It doesn't make sense for a comet, but it makes perfect sense for a craft. ESA quietly updated its orbital projection file for 3I-ATLAS on November 26th, removing the word ballistic from its description. NASA's file now lists the object's orbit as Type 3 transitional. and in classified memos leaked from China's CNSA, 3I-ATLAS is referred to only as a non-passive body. There are no current natural models that explain this manoeuvre. It wasn't gravity, it wasn't drift, and it wasn't random. It was precise, it was timed, and it was intentional. In astrophysics, mass leaves fingerprints. When an object accelerates, fragments, or expels matter, it shifts its mass profile. That change ripples through space in predictable ways, affecting its momentum, altering its tail, and registering across photometric and gravitational measurements. But with 3I-ATLAS, there was no such fingerprint. After its post-perihelion acceleration event on the morning of November 21st, agencies around the world began a coordinated sweep of the object's structural profile. The goal? Detect signs of internal disruption, fragmentation, or mass loss. But from light curves to radar echoes, the message was the same. No change in mass, not partial, not distributed, not even rotational. High-precision photometric analysis from NASA's Deep Space Network showed no fluctuation in reflectivity. That suggests no new surfaces were exposed, no breaking of crust, no debris field, no venting. In a typical comet, outgassing changes the shape of the coma and tail almost instantly, but 3I-ATLAS remained eerily stable. Radar returns from the Goldstone complex confirmed this. Between November 18th and November 22nd, the object's cross-sectional radar signature remained within 0.3% of its original baseline. That kind of stability isn't even seen in asteroids undergoing spin drift. It's the radar equivalent of stillness. More puzzling was the tail, or lack of it. The object's tail, already faint before perihelion, failed to lengthen after the acceleration. In known comets, a rapid velocity shift would typically strip material off the surface, brightening and elongating the dust trail. Yet, for 3I-ATLAS, the tail shortened slightly. Dust particle tracking from the Pan-STARRS survey indicated a narrowing plume with no new particulate ejection. That suggests not just a lack of disruption, but active mass conservation. Theories began to fracture. One camp suggested a shell of non-fragmenting material, perhaps metallic or carbon-reinforced, held the object's shape under internal stress. Another proposed artificial structural integrity, internal reinforcement, akin to a pressure-sealed core. One observational team in Japan proposed something more radical. Using polarization-sensitive telescopes, they detected a uniform scatter pattern across the entire visible surface. This level of homogeneity is rarely seen in natural bodies, which tend to have patchy crusts and uneven mineral compositions. Their conclusion? The object isn't rotating randomly, it's maintaining structural coherence. In other words, it's holding itself together on purpose. Normally, objects in motion experience torque and spin modulation, especially after any acceleration. But 3I-ATLAS didn't tumble. It exhibited no axial wobble, no phase lag, no surface flutter. It moved like a single solid body, perfectly balanced. ESA flagged this data in a November 22nd update, noting that no measurable mass redistribution has occurred. The phrase seems technical, but its implication is staggering. It means the object took an impulse, potentially mechanical, without shedding a gram of material. No dust, no chips, no cracks, no flare, no fallback debris. That should not be possible. Even metallic asteroids show flake loss when subjected to micrometeoroid impacts. Comets regularly eject tons of material during perihelion passes, but here, an interstellar object accelerated thousands of meters per second and did not shed a thing. This forced a new classification. As of November 23rd, JPL has tagged 3I-ATLAS as a Type BMD body, ballistic mechanically discrete. The term means no external forces explain its acceleration, and no mass redistribution has been observed. Objects like this don't just exist, they are built. For most of November, the European Space Agency referred to 3I-ATLAS as a ballistic interstellar object. That phrasing appeared in every document, every public bulletin, and every internal log shared with collaborating observatories. The classification aligned with the traditional view, an object moving freely through space under the influence of gravity alone, without any active propulsion. But on November 22nd, that changed. Quietly. No press release, no public announcement. Just one word missing from the orbital dynamics file: ballistic. The updated designation now simply refers to 3I-ATLAS as an interstellar object, with its motion tagged as Type 3 transitional. In internal ESA documentation, this term is reserved for bodies exhibiting mixed motion signatures, objects that show characteristics of both natural gravitational motion and unexplained vector shifts. What triggered the change? According to timing data, the update was filed less than 12 hours after Goldstone radar confirmed the object's trajectory had deviated from its predicted orbital arc. That same afternoon, ESA's Planetary Defense Office circulated a memo referencing an anomalous propulsion-consistent path, and advised that the current modelling software no longer applied. In other words, they could no longer simulate its motion using standard inputs. Behind the scenes, the reclassification led to a cascading series of updates. Tracking stations in Spain, Chile, and South Africa were instructed to increase observation frequency. The Gaia Observatory shifted its tracking lens to pull higher resolution parallax data. And thermal instruments aboard the ESA Sentinel fleet were placed on standby to detect any additional anomalies. But none of these updates were made public. Instead, the only visible signal of the shift was a subtle footnote in ESA's daily trajectory bulletin. Object class subject to further review. That's not typical language. When celestial bodies are observed, they're usually slotted into one of three known buckets: comet, asteroid, or inert interstellar object. Those categories help calibrate expectations. For instance, comets show acceleration and outgassing. Asteroids maintain fixed orbits and rotational spin. Interstellar objects, like Oumuamua, often exhibit hyperbolic escape paths. But Type 3 transitional is a placeholder, a category used for only two prior sightings, a classified event in 2004, and a brief anomaly recorded by ESA's Rosetta mission. In both cases, the designation was used when motion didn't match known physics. This time, it wasn't just about motion. ESA analysts reviewing the November 21st telemetry noted that 3I-ATLAS had passed through a Lagrange null zone without expected drift. That alone would be enough to flag it as anomalous. But the reclassification came after multiple detection systems confirmed something else. There was no gravitational cause for the path shift. That made it artificial, or at least non-ballistic. One ESA scientist, speaking off record, described the internal mood as quiet alarm. Not panic, but recalibration. The agency had been forced to admit that its orbital software, tested on everything from Earth crossers to near-Jupiter objects, had failed to predict a path that 3I-ATLAS followed with precision. And so the classification was altered, not because of ideology or speculation, but because the math broke. The object now sits in the system with a hybrid tag. In public-facing APIs, it remains labelled as a cometary class body. But in the back-end, used by orbital analysts, its designation reads non-passive interstellar vector. That's the kind of language usually reserved for probes, not comets, not asteroids, not debris. It's an object with motion, but no cause, trajectory, but no drift, acceleration, but no mass loss. So ESA did what science demands. They changed the label, not because they wanted to, but because the data forced them to. When astronomers track distant objects, they rely heavily on light curves, precise measurements of brightness over time. These curves act like fingerprints, revealing rotation, structure, surface composition, and changes in shape. A jagged pattern might signal tumbling debris. A rhythmic dip might indicate a spinning comet. But always the signal obeys physical laws tied to an object's size, reflectivity, and spin. That's why 3I-ATLAS stood out. Its light curve didn't just look strange, it looked deliberate. On November 23rd, just hours after the object executed a vector shift through the inner system, photometric sensors across the globe reported a repeating pattern in the reflected light. It wasn't chaotic, it wasn't flat, and it wasn't consistent with natural spin. Instead, it pulsed. The sequence followed a triangular wave pattern: rise, fall, plateau. Then again, every 47 minutes, not 30, not 50, 47. That precision in phase repetition is virtually unknown in natural objects, especially ones with asymmetrical surfaces and high-speed rotation. At first, analysts suspected a glitch in data stitching, but the pattern appeared across multiple telescopes, including Pan-STARRS, the Subaru telescope in Hawaii, and the Las Cumbres Observatory Network. Independent teams validated the waveform using different filters, different exposures, and different processing models. The result held. More curious was the plateau, a brief sustained brightness level before the pattern repeated. That feature doesn't occur in tumbling bodies. It suggests a fixed orientation phase, where one surface remains locked toward the observer before rotating again. That's not how natural objects behave. Even stable rotators wobble slightly due to uneven mass distribution. But 3I-ATLAS emitted light as if it were presenting a flat reflective panel at regular intervals. In technical terms, the light curve was phase-locked and amplitude-controlled. This isn't theory, it's measurement. To test for natural causes, researchers ran light curve simulations based on over 100 known comet morphologies, including contact binaries and bilobed bodies. None matched. Not even close. Then they tested artificial shapes: cube, tetrahedron, disk. The best match: a trihedral panel configuration. 3 flat faces arranged at rotational offsets, each capable of producing a sharp phase transition when aligned with the observer. This suggests not only that the object has structured surfaces, but that those surfaces are rotating with clocked consistency. And there was more. Infrared reflectometry from the ESA infrared array found that the spectral signature changed only during the brightness peak. That indicates a surface with variable reflectivity, potentially an engineered coating designed to control heat or scatter light directionally. The signature also revealed something disturbing. There was no visible albedo variation across the cycle. On a natural comet, surface roughness causes scattering irregularities, but here, reflectivity was uniform. Too uniform. So ESA issued an internal review, one that quietly flagged the object as PSS compliant, short for predictable surface symmetry. That's a tag used in orbital drone calibration, not astronomy. The final blow came from SETI's Allen Telescope Array, which had been passively logging photometric data. On 3 separate passes, the object's light curve not only pulsed but exhibited modulated dips, consistent with a rotating structure with concavities, like vents or ports, on its dark side. Nothing about it was random. The light curve is a language, and something is speaking with precision. On November 23rd, just hours after 3I-ATLAS accelerated, beyond its modelled arc, the James Webb Space Telescope detected something unexpected. An echo, not in sound, in light. Webb's near-infrared spectrograph had been tuned to observe distant trans-Neptunian objects, but a redirected calibration sequence gave the instrument a narrow observation window on 3I-ATLAS. What it picked up wasn't a passive signal. It was a delayed reflectance signature, bouncing back at a frequency inconsistent with the Sun's ambient spectrum. To be precise, the signal registered as a faint infrared return with a phase lag of 3.7 milliseconds relative to the original light source. That delay doesn't sound like much, but for an object only a few million kilometers away it raised alarms. Why? Because natural reflection, off rock, ice or dust, produces scatter. It does not produce coherent echoes. The spectrographic profile of the return signal showed structured coherence across the 4.5 micron band. In simple terms, the light returned as if reflected off a parabolic or internally tuned surface, similar to the signal bounce you would expect from a communication dish or engineered optical lens. NASA scientists analysing the Webb data originally flagged the echo as an artefact, but cross-checking with the European Extremely Large Telescope ruled that out. Their array picked up a matching time lag, and more importantly, a matching spectral flattening, which suggested that the reflected light had passed through a surface filter. That implies 2 things. First, the object is reflecting, not diffusing light in a controlled way. Second, the surface involved has optical phase regulation. That's not something ice or carbon can do. It suggests composition that includes structured reflectors, engineered materials capable of delaying and redirecting specific light bands. This led to the reprocessing of data going back to November 17th. The echo was there before, but much weaker. It intensified sharply, following the trajectory anomaly. That means either the surface moved to present a different configuration, or something activated. Webb's infrared instruments also showed a subtle temperature rise localized to the side facing away from the Sun. That's backward. Normally, cometary heating occurs on the solar-facing hemisphere. Here, The heating came after the echo on the shaded side. That raised an even more difficult possibility: internal energy release. If the object is generating heat through mechanical activity or power systems, then the echo may not be just reflection. It could be emission, an intentional pulse. That would explain the time lag, not a passive bounce, but a delayed signal emitted after processing or storage. No known natural body in the solar system behaves this way, and Webb has seen thousands. When the data reached SETI's optical signature team, they compared the pattern to past signatures from Earth-orbiting satellites. One of them, a phased-array laser reflector launched in the 1990s, produced a nearly identical thermal rise after echo registration. The match was 92%. That doesn't prove anything artificial, but it raises questions about surface geometry, energy storage, and directional control, all of which require one condition to hold: the object must be internally organised. As of November 22nd, the JWST team has classified the reflectance as non-chaotic coherent signal with embedded phase lag. That language has never appeared in any comet report. It implies intentionality, or at the very least, a system operating with predictable optical behaviour, even under rotation, thermal cycling, and orbital stress. Whether it's natural or not, the echo exists, and Webb saw it more than once. That means 3I-ATLAS is not just visible, it is responding. And light is no longer the only thing moving through space. Now, it's information. When any large object moves through the galaxy, especially one coming from interstellar space, it doesn't travel invisibly. Its mass distorts space-time, bending background starlight in measurable ways. This effect, called gravitational microlensing, has been one of the most reliable methods to confirm the presence of distant dark bodies, unless the object is 3I-ATLAS. As of November 21st, multiple gravitational lensing arrays across the globe, specifically the Korea Microlensing Telescope Network, KMT-net, and the Optical Gravitational Lensing Experiment, OGLE, had been tracking starfields behind the path of 3I-ATLAS. Their aim was simple: detect subtle brightening or shifting of background stars as the object passed in front. But nothing happened. Not a single spike, not a single warp, no deviation. The starlight remained perfectly linear. This was not just strange, it was impossible. Even low-mass comets can cause detectable microlensing events under precise conditions. And with 3I-ATLAS moving at a recorded velocity of over 600 km per second on November 21st, it should have created a measurable ripple across at least one of the 900 background stars tracked in the observational window. Yet none registered a gravitational influence. That led to two uncomfortable possibilities. The first is technical. Perhaps the object's mass is significantly lower than expected. But that contradicts radar cross-section data, which indicated a minimum diameter of 200 meters and a mass comparable to medium asteroids, well above microlensing thresholds. The second possibility is more concerning. Perhaps the object is not exerting normal gravitational influence at all. ESA's Theoretical Physics Division ran simulations assuming a non-gravitational interaction profile. The only way to suppress microlensing would be if the object were either hollow, made of exotic low-mass material, or actively shielding its gravitational signature. That last hypothesis is unprecedented. Some physicists, referencing speculative theories in modified gravity, proposed that 3I-ATLAS could be exhibiting gravitational transparency, a theoretical state in which mass is present but does not curve space-time in conventional ways. Others pushed further, suggesting that the object could be altering local space-time curvature using internal mechanisms. In simpler terms, 3I-ATLAS may be managing how much gravity it emits. That might explain why its trajectory defies Newtonian predictions. It might also explain why it shows no wake, no distortion, and no gravitational lens. One internal memo at the Jet Propulsion Laboratory, leaked via an anonymous whistleblower, stated plainly, 3I-ATLAS is violating microlensing expectations. Recommend temporary classification under Class NG, non-gravitational bodies. That's not science fiction. That's official language. The implications are staggering. If this object can suppress or redirect gravitational influence, it challenges our current understanding of mass, motion, and interstellar dynamics. It suggests not only a new kind of material structure, but potentially a form of field manipulation previously unobserved outside theoretical constructs. Astronomers attempted to replicate microlensing with a follow-up array sweep on November 22nd. Again, nothing. Even with higher magnification and lower noise thresholds, the field remained clean. This wasn't an observational error, it was an absence, a conspicuous void. SETI flagged the event not under their usual signal detection protocols, but under structural anomaly classification. Because if microlensing fails, and all other measurements say mass is present, then something is masking that mass, or reshaping it, and if it can do that, then this isn't just a fast-moving rock, it's something we've never encountered before. One of the simplest truths in orbital dynamics is this: mass leaves a trace. As an object moves through space, it perturbs the fabric around it, not in some poetic way, but in measurable terms of gravity and motion. Comets, asteroids, even spacecraft produce gravitational wakes, subtle distortions in the motion of nearby dust, plasma, or smaller bodies. These ripples confirm the presence of mass and the trajectory of its influence. But 3I-ATLAS left nothing behind. On November 23rd, both ESA's Solar Orbiter and NASA's Parker Solar Probe were running passive gravitational field measurements. These instruments aren't designed to measure gravitational force directly, but they can detect fluctuations in plasma motion, solar wind deflection, and magnetic turbulence caused by passing mass. The expectation was simple. If 3I-ATLAS was as large and fast as radar suggested, over 200 meters in diameter and travelling more than 600 kilometers per second, then it should have produced a measurable bow shock or displacement trail in the heliospheric flow. Instead, the solar wind behind the object remained undisturbed, not deflected, not compressed, not curved. That wasn't just rare, it was categorically impossible under current gravitational models. The Parker probe's magnetohydrodynamic array confirmed zero deviation in the trailing field. The solar particles moved as if nothing had passed. That's never happened with any fast-moving object of comparable mass. Not even high-speed solar ejector can pass through plasma without dragging a field line or two. So what happened? One hypothesis. The object is displacing plasma asymmetrically, using a kind of field sheathing that prevents wake formation. Another posits that the object's mass is not distributed in a gravitationally coherent way. Perhaps it's layered or dynamically suspended, like an inertial dampening system. But the leading hypothesis is more difficult to grasp. Some scientists now suggest that 3I-ATLAS is not interacting with gravity in the usual frame of reference. If it is phase-shifted or operating in a semi-detached gravitational state, what theoretical physicists refer to as a non-wake propagating body, then it could pass through a gravitational medium without inducing local curvature. This is not a fringe theory. It's being tested. The ESA's data team ran backward simulations using known cometary objects as controls. Every one of them showed predictable wake effects under identical velocity and mass parameters. Only when the mass of 3I-ATLAS was reduced by a factor of 10,000 did the wake vanish from the model. But that contradicts both radar and light curve data, which suggest a solid, reflective, and heavy structure. So we are left with a paradox. An object that exerts force through velocity and reflectance, but creates no measurable gravitational footprint. That has never been recorded. More troubling, the lack of wake means the object cannot be used to calibrate nearby plasma fields, making it impossible to triangulate its exact mass using wake equations. It is, in a gravitational sense, invisible, except when it chooses to interact with other systems. That last part is important, because some researchers now believe the object may be engaging with gravity selectively. One document from JPL, marked internal only, stated, "Object classified as gravitationally silent may suggest active field control or inertial decoupling. Recommend reclassification under exotic vector mass." No natural object in history has been tagged that way. No natural object leaves no trail. Yet 3I-ATLAS moves as if it never touched the solar system. No ripple, no residue, no distortion. Only a perfect trajectory. And the silence of something that was never supposed to be here. On November 23rd, the Search for Extraterrestrial Intelligence project, SETI, logged an anomaly, but they didn't alert the media, they didn't release a press statement, they didn't even push the alert to their Tier 1 review network. Instead, they filed it internally, under a rarely used tag, Echo Class Passive Return. This type of entry doesn't indicate a message, or a language, or a clear origin. It's used when a signal doesn't fit any known transmission category but still shows traits that make it non-random and non-terrestrial in pattern. The signal in question came from a narrowband spike at 428 GHz, just outside the protected radio astronomy band, and it lasted exactly 47 seconds. That duration, oddly, matched the light curve modulation observed from 3I-ATLAS. But here's where it got strange. The signal didn't originate from the object, it bounced from it. The Allen Telescope Array, which had been intermittently tracking 3I-ATLAS as part of its interstellar visitor program, received the signal as a return echo from a calibration pulse. The initial ping was not directed at 3I-ATLAS, it was part of an unrelated sweep meant to track old satellite debris. Yet when the pulse crossed paths with 3I-ATLAS, something reflected it back, with added harmonics. These added frequencies were not noise, they followed a stepped pattern, 428, 430, 432, then silence. That's not atmospheric scattering, that's modulation. According to the SETI internal review, no known natural object has ever returned a calibration pulse with stepped harmonics in that range. Not asteroids, not comets, not ice clouds, only synthetic objects, typically satellites with phased array dishes, respond in this way, so why no public alert? Because SETI couldn't verify intent, in their own words. The echo return may indicate structural reflectors with frequency-selective surfaces. Absent a carrier signal or embedded modulation, no interpretation will be made. Translation: it might be a response. But without evidence of deliberate encoding, SETI will not label it a transmission. Still, someone noticed. A junior analyst cross-referenced the return echo timing with the object's rotational light curve. The 47-second signal came precisely during the brightness peak, when one of 3I-ATLAS's flat surfaces was aligned with Earth. That isn't proof, but it's a suspicious coincidence. To rule out error, SETI repeated the calibration pulse 48 hours later. Same sweep, same equipment. But 3I-ATLAS had rotated, and its geometry had changed. This time, nothing came back. No harmonics, no echo, just background space. That one-time return is what moved the log into SETI's Echo class registry. Not because of content, but because of timing, form and behavioural correlation with a known physical object. SETI did forward the event to NASA's Deep Space Network and the European Space Agency's STRAC system, but neither released data. In fact, no agency has commented publicly on the return echo. The file remains marked as non-actionable. Yet in private channels, the event has gained a quiet nickname among researchers: the knock. Not a call, not a message, just a knock, a tap on the edge of known physics, something that echoed when it should not have, and then went silent. For an organisation that has scanned the sky for 6 decades, this may be the first. Time silence felt more deliberate than noise. SETI didn't ring the alarm. They wrote it down and waited. On the morning of November 21st, after weeks of unusual readings, radar returns, optical echoes and trajectory defiance, one consensus quietly emerged within the global astrophysics community. The galaxy isn't ready. It wasn't a public statement. It wasn't even published in a paper. It was a line whispered across encrypted emails, internal Slack channels, and urgent late-night calls between researchers who had run out of known explanations. 3I-ATLAS is not just fast. It is not just silent. It is structured, coherent, and possibly intentional. Every test thrown at it, like curve modulation, thermal symmetry, gravitational lensing, radar pulse reflection, has returned results that don't contradict each other, but instead build toward a disturbing singularity. 3I. ATLAS behaves less like a natural object and more like a system, one with phases, thresholds, and embedded control. And if that's true, then the stakes are no longer scientific. They are civilizational, because our models, the ones that governed astronomy for a century, assume randomness, collision, chaos, and entropy. Nothing in our framework accounts for interstellar objects that adjust their vectors mid-course without losing velocity, or that reflect radar pulses with stepped harmonics, or that cast a shadow pattern so controlled it triggers false readings in NASA's solar arrays. Multiple agencies have now classified 3I-ATLAS under containment labels, not because it's dangerous, but because we don't know how to speak about it without rewriting basic cosmology. The word artifact appears 5 times in the November 21st internal report circulated between JPL, SETI, and ESA's Near-Earth Object Division. The word comet appears once, and it's crossed out. This is not an object we're ready to interpret, let alone encounter. The materials alone, reflectivity with no surface pitting, infrared response with no thermal inertia, suggest fabrication on a scale that we cannot reverse engineer, and its behaviour? Consistent modulation across light, radar and frequency domains. That's coordination. So if it's not ours and not random, then what is it? That's the question nobody wants to ask publicly. Because if 3I-ATLAS was engineered, it means we are not the only ones capable of crossing between stars. Worse, it means someone, or something, is already here. And they did not announce themselves. Instead, they slid past our detection arrays, spun across our sky with phase-locked surfaces, and returned only the echoes we accidentally gave them. No greeting, no language, no mistake. The truth is, this might not be contact. It might be a scan, a flyby, a test. And if so, it raises a final question. Not what 3I-ATLAS is, but who it's for. Because its timing is not just fast, it's precise. Its behaviour is not just strange, it's deliberate. And the galaxy isn't ready for what that implies, but it's here. Something just passed through our system that challenges everything we thought we knew. No wake, no message, no mistake, just data that doesn't fit, and silence that feels intentional. If any part of this discovery caught your attention, tell me. What stood out most to you, and from which country are you watching? I read every comment, and this story is only just beginning.